Hello, my name is David Themens, and I'll be talking today about the decade of ionosonde observations that we have at the Canadian Higher-Tech Ionospheric Network, or CHAIN. I'll start off with a brief overview of the CADI, or Canadian Advanced Digital Ionosonde operations in Canada, before talking about CHAIN and the GNSS and Ionosonde data products that they provide. I'll then talk about or put that data record into context with respect to the long-term data record that we have already existing in Resolute prior to CHAIN. Finally, I'll just finish up with a discussion about one of the main kind of thrusts of this presentation, which is this manually scaled data record at Resolute, which I'm hoping to make openly available to the community. And as part of that, I've done a number of assessments of its precision and accuracy. So prior to CHAIN, John McDougall operated a number of Canadian Advanced Digital Ionosondes in the Canadian sector, given by these dots and crosses here and here, as part of the Canadian Geospace Monitoring Program, which began in 1995. Fast forward to 2009, CHAIN was developed and took over operation of the Eureka, Resolute, and Cambridge Bay CADI systems that were originally deployed by John McDougall, and expanded to also include a number of systems in Pond Inlet, Hull Beach, and Iqaluit. All of these systems would be co-located with scintillation quality GNSS receivers, and a number of additional sites with just these GNSS receivers were also deployed. Moving further ahead to 2014, with some funding from the Canadian Space Agency, CHAIN expanded to include a number of additional GNSS receivers spanning not only the Polar Cap, but also the Auroral Oval. These are 15 new sites at this point. Going further to 2018, with some funding from Defence Research and Development Canada, CHAIN expanded to include 3 additional Ionosonde sites at the Sax Harbor, Rankin Inlet, and Kiktarjuak, all again co-located with GNSS receivers. And in 2019, we also deployed this development site here in Blissville for testing of an experimental SDR-based Ionosonde. GNSS. The original 10 sites operated by CHAIN logged GPS L1 amplitude and phase at 50 Hz in real time, and also provide telemetry content at 1 Hz. The 2014 expansion sites, which use newer Septentrial PolarX Pro receivers, log GPS L1 and L2 at 50 to 100 Hz, with telemetry content regularly provided at 1 Hz, but with capacity to create telemetry content at even up to 100 Hz. There are also plans in the works to log Galileo and GLONASS as well, now that we've upgraded to newer cellular comms. The CADI systems operated by CHAIN generate ionograms every minute, where this is generally a higher sampling than is typically used by Ionosondes. But this allows us to properly characterize patches and TIDs that are regular structures at high latitudes. CADIs use 2 pairs of orthogonal dipoles arranged in a square to discern polarization and angle of arrival or direction of arrival. And using those measurements in combination with a number of fixed frequency broadcasts, the Ionosonde is also capable of providing drift measurements, or 3-dimensional drift measurements of the plasma every 30 seconds. This is just an example of one of the Ionosondes here, I think in Pond Inlet, where you can see a central mass supporting our transmit delta, and a number of our dipoles here on the ground arranged in a square for our receive. This is just an example of the meridional drift in black and the zonal drift in red, derived from the CADI system in Resolute during the period ahead of and including the 2013 St. Patrick's Day storm. And here we just have an example of an ionogram from, I think this is Cambridge Bay, where we're plotting the rainbow is the ordinary mode given here, and the black is the extraordinary mode. So we log these ionograms every minute. And unfortunately, as some of you might know, when operating an ionosonde at high latitudes, conditions are not particularly conducive to being automatically inverted or automatically scaled. Because of this, Chain doesn't employ an automatic scaling software, and so all of our data needs to be manually scaled. To that effect, I have over the years scaled about 627,000 ionograms from Chain, which I keep on my my laptop and a cloud backup just for safety's sake, which have all been inverted using pull-in. And if you'd like any of that data, you're free to just send me an email, and I'm happy to provide you with that, or to provide you with specific requested periods that I can scale for you. And one of the main things that I want to get across with this presentation is that I plan to publicly release this data set sometime in summer of 2021 for the Resolute Ionosonde. One of the reasons to do this for Resolute is that Resolute has one of the longest Ionosonde records out there, where we have manually scaled data, Resolute dating back to 1949 all the way to the current date. Where in black here we have the historical record of Resolute from the old analog Ionosondes, and then from 1995 on we have data from the Canadian Advanced Digital Ionosondes, where we actually have a chain all of the original ionograms from John McDougall's CGSM sites. In red, we have the manually scaled record, where I've started mostly from the initial operations of the chain onward, but I've recently started going back to the 1995 and working my way forward from there to try and complete this record so that we have a nearly continuous time series of ionograms at Resolute dating back to 1949. And hopefully this will enable a number of interesting studies, particularly with the interest recently in long-term trends in the ionosphere. This is just an example of the FOF2, or the peak critical frequency of the ionosphere, for all of these years. Blue being the old Ionosonde before Caddy, and then red being the manually processed data after the Caddy, or once the Caddy was deployed. Now, I mentioned that autoscalers aren't particularly great at high latitudes, and kind of asked you to take my word on it. But to give you an example, we can kind of just go to our neighboring Ionosonde in Kanak-Thule, where you can look at the manually scaled and auto-scaled data from that site. Red here is the auto-scaled data, and the black is the manually scaled data. And really what I want you to take away here is that, anytime there's an interesting feature in the pore cap, it's very likely that an autoscaler will fail to capture that feature. So if you're using an Ionosonde for a case study, particularly during disturbed periods, that there's no alternative to manually processing that data. Find someone you know who's familiar with these data sets or familiar with Ionosondes, and just get them to help out. Otherwise you can end up in situations where you publish a paper and with inaccurate data, which might have you draw incorrect conclusions about that data. Now, one thing that tends to happen to me is when I'm when I'm a reviewer, is I'll say, well, you should use manually scaled data, and the response will be, well, do you know how precise or how accurate manually scaling data is? I'll submit a paper to a journal, and I'll have a reviewer come back to me and say, well, you say this manually scaling data is really accurate, but to what extent? So there are a number of ways that we can assess the precision and accuracy of Ionosonde data. One of which is one that I do pretty regularly, about twice a year. I'll randomly select a number of days that I manually scale multiple times in a row. So I'll scale the same ionograms 6 to 10 times for a particular day, where I've spread out the scaling of those ionograms so that I don't scale the same ionogram twice within the same day. And then you can just look at the distributions of the deviations in FOF2 from the mean for those rescalings of the same ionograms, or similarly for HMF2. And this gives you an indication of the precision with which the person, or the consistency with which the person is scaling those ionograms. When you do this, this is just an example of one of those scaling periods I've done, where we have a standard deviation in FOF2 about 0.08 megahertz, which is on the order of the instrument's precision, the actual voxel or pixel size. And on the right, we have the same thing for HMF2 with a standard deviation of about 4.1 kilometers, which is about 2 kilometers less actually than the pixel size or the resolution of a CADI system, which is 6 kilometers. Another thing we can do to assess the precision of this data is to scale it at very high sampling rates. So in this case, 1 minute sampling, and then just take a window, in this case 5 minutes, around that data and look at the variability of the scaling within that window. That variability will be composed of two things: the scaling precision, as well as natural variability in the ionosphere on 5-minute timescales. And when you look at the distribution of those, the FOF2 and HMF2, when doing this during the, again, that period during the 2013 St. Patrick's Day storm, you'll see that we end up with standard deviation FOF2 of about 0.15 megahertz and HMF2 on the order of 5.8 kilometers. So this sets an upper bound on the precision of the FOF2 and HMF2 from these systems, or from this manually scaling. Another thing we can do is compare the CADI data to incoherent scatter radar. We have a riser, or we have the riser system at Resolute, which we actually calibrate, or that is calibrated with CADI observations. So we can't use can't use the ISR to compare FOF2, but we can use it to look at HMF2. And when you do that, you find that there's a median difference between the ISR and the CADI of about 2.8 kilometers, with a standard deviation of about 20 kilometers, where this 20 kilometers is composed of the scaling precision, which we know to be somewhere less than 6 kilometers. The collocation errors or differences between the fields of view of the riser and the CADI system, and the precision of the incoherent scatter radar's HMF2 estimate, which should range between 5 and 15 kilometers, depending on the altitude of the F2 layer at that time. This is just an example of FOF2 or NMF2 and HMF2 from CADI in red and ISR in black for a period in February 2011, where you can see there's considerable agreement between the ISR and the CADI observations. All this to say, Chains operate a comprehensive network of GNSS and Ionosonde instruments within the Canadian sector for over a decade. And while autoscaling isn't available, I've manually processed a good amount of this data, and I'm happy to manually process more for anyone who would like to work with these instruments. This will be publicly released. The entire database for Resolute will be publicly released sometime in 2021. To complete this manually scaled data record at Resolute dating back to 1949. Furthermore, manually scaled data is highly reliable with precisions at or near the ionogram resolution level. With that, I'd just like to say thank you. I'll leave up the link to get chain data, as well as my email in case you'd like me to scale some periods for you. Thanks.